Great, thanks so much. So can everybody see my screen at this point? Good, okay. So what I'm gonna do is just take us through a couple new features in PixPlot, which is Yale's open source large visual collection visualization tool. Some of you may have seen demonstrations of PixPlot at Fantastic Futures. I'm going to show you a new PixPlot that my colleague Kathy DeRose built on about 13,000 images that are from the Smithsonian's open access collections. And I'm sure that Rebecca and others on the call from the Smithsonian can talk about the long process that was involved in getting all these 13,000 images open access. You can see they're really diverse and really represent the breadth and depth of what's at the Smithsonian Institution, both in their scientific and the cultural heritage spaces. Again, the idea with PixPlot is that what we want to do is not just look at these things one by one, but we want to look at about 13,000 images according to visual similarity. And so what I'm going to do now is shift the visualization into that. You can see that we have this kind of cluster, a kind of constellation, or maybe like an archipelago, in which visually similar images are next to each other. And this is, for example, all these paintings of churches and things like that end up kind of around each other. This is a 2D projection of a originally 2048 dimensional space, which is the penultimate layer of a pre-trained captioning network. We cut off that last layer and we use the semifinal layer and we project it down. My colleague Kathy has annotated a lot of these clusters. So I've clicked on the thing that I think is jewelry portraits over here. I could also click on a different cluster, which might be something like drawn portraits, and we'll go to a different part of the network. As we get interested in the particular drawn portraits, we can click on them. And of course, what we can do is we can always click on the permalink, which will take us to the holding institution, the Smithsonian, and let us understand more about that. There's nothing too different about PixPlot so far, what I've shown you. This is a very diverse collection. Here we're arranging it according to Mario Klingerman's raster fairy layout, which keeps things in a grid, but sort of shows you some of the local clustering even in a grid format. People often ask us, okay, well, you've got these 13,000 images from the Smithsonian Institution. It's very diverse, it clusters very well. What about more domain-specific things? For that, I would show you a new demonstration we're doing around 2,200 automobiles that were excerpted from the photography of Ed Ruscha. Have people heard of the American pop artist Ed Ruscha? He did the building, Every Building on the Sunset Strip, and other important sort of pop art deadpan books starting in the 1960s, originally from Nebraska, came to LA, took a lot of pictures of streets in Los Angeles. We used a semantic partitioning network to extract just the automobiles from Ed's photography. And so what we have is just a bunch of cars. Seeing them in a grid is, of course, not too exciting. What we want to do is we want to go ahead and cluster them according to visual similarity. So we're going to do this on a very restricted domain of automobiles. And you could say, well, does this really still work? And the answer is yes. All of my Volkswagen Beetles and things that look kind of like Volkswagen Beetles appear in this cluster over here. Jaguar E-Type, other things that are vaguely Volkswagen-like. We have a collection of two-door fuel-inefficient coupes, which we're calling Malaise coupes from the 1970s here. These all cluster quite well. And then, of course, minivans are all over here in the bottom left. This is not a network that knows anything about Beetles or minivans. It's just a generic network, but the idea is to show you how sort of the morphological similarities and differences in automobiles can be visualized according to machine learning algorithms. We can also change the dates that we're looking at. Very few minivans in the 1970s, but more when we turn on the 90s and 2000s. So there's an example of a more domain-specific problem of automobiles. And I want to show you three brand new features that are kind of exciting that people have, in fact, nobody's seen before except for you guys. So here I'm going to go away from the streets of Los Angeles, and I'm going to take us back to everybody's favorite European capital, Oslo. We're going to go here and look at a new version of the visualization that I showed at the Fantastic Futures conference in Palo Alto. This is our standard images of the Norwegian capital from the 1860s to about 1900. Political illustrations here, pictures of people on the street. These are all the same sort of collections you've seen before. What's new is that we're now visualizing cluster membership. So you can see, let me make the visualization a little bigger here. When I move my mouse on the left of my screen, you can see that we're now showing the various clusters that are in this k-means sort of sorting. So here's my collection of Norwegian priests, all of whom have this very specific collar on the screen. We saw that in Palo Alto. But you can now sort of get a visualization of how large that cluster is and how many things are really a part of it. This is not the final step. It's an important first step in making some of these models interpretable and seeing what parts of the cluster are actualized by this particular form of clustering. So you can see as I move my mouse over it, you get different parts, sort of nations of different images. That's really exciting. We're still working on the user interface for this. We're trying to figure out what makes the most sense, but we think it's now pretty clear what the portrait cluster is by looking at that overlay. Other new features, which I know are going to excite some people in the room, have to do with two things at once. So we're going to have to follow me as I go down two paths simultaneously. I'm going to talk about both IIIF manifest ingest, and I'm also going to talk about real-time analysis of images in your web browser without having to run PixPlot on a deep learning workstation beforehand. So I'm going to try to do these both at once. Here I have on the screen some kind of document, some kind of Latin thing. Well, some European will have to tell me exactly what this is. It's a multi-image IIIF manifest. And you can see I can inspect just using the IIIF viewer that's part of this Swiss website. Each page in the manifest, I can look at it, I can zoom, I could probably pull these some into Mirador if I were that kind of guy. The important thing is the manifest contains these dozens of images here. And if I really want to see how many images are in this IIIF manifest, of course, I can paste the manifest into my web browser. And what I can do is take a look at what's actually in this JSON file. So if I scroll down, you'll see here's one image, here's another one. All of these are JPEG 2000 links. It's all good. So now I'm going to put all this together. And what I'm going to do is show you a very early alpha version of a new version of PixPlot, which actually uses that same JSON that we've been looking at, that kind of code in my web browser, which includes 451 images. We're going to load those images from the IIIF manifest. We're actually going to load the ImageNet model in my web browser, and then we're going to have PixPlot arrange all of the images from that manuscript so that things that are visually similar are near to each other. And so what we're seeing is all of the book binding pictures. Here's a picture of the spine, the edge of the book. Here's one with a color chart, one without a color chart. There's all in the same neighborhood. And in fact, the two images with color charts on them are near each other. Those images look really different from the images over in the top left, which are these kind of more color plates, full illustrations. I don't know the technical language for this 15th century document. And those beautiful color images at the top left look very different from some of the more traditional manuscript pages here at the bottom right, which are kind of more sort of litanies and sort of descriptions of just things in handwriting. Again, what we're doing here in real time is pulling in 451 images from a given IIIF manifest. We're loading the ImageNet, the MobileNet model into my computer's, my web browser's RAM. We're using JavaScript and sort of TensorFlow in the JavaScript layer to arrange the images which are visually similar in this IIIF manifest around each other. Now, this is a sort of really early alpha test. It doesn't have all the affordances of PixPlot that you normally see. It doesn't have that cluster membership, doesn't have the click to zoom to the full window. But it's a kind of, and we certainly don't think that this alpha quality code would scale to the level of 13,000 images from the Smithsonian or 30,000 images from Oslo. But we are interested in pushing the limits of what could be done with this particular code base, not only for the use case of having 451 images from a bound book or a manuscript that's then been bound, but also for other real-time visualizations of data into PixPlot in ways that are not predictable. So what's a great example of this would be a search engine result. Let's say you run a digital library system for a museum or for a library, and you say that the user has typed the word horse into your full text search. And you're doing the best you can, you're doing TF-IDF, you're doing search weighting, you're trying to give them the horsiest horses that exist in your library or in your museum. But we know from user experience studies that nobody clicks beyond the first page and nobody looks at the 80th page. And so if we do have maybe a couple hundred images or books that are about horses, what we might be able to do with this real-time analysis of images that doesn't need you to run PixPlot for like on thousands of images over the course of 20 minutes, is actually present a kind of cheap and cheerful real-time PixPlot visualization of all the visual objects which were returned by a sort of given textual search for something like horse. And that might help the user understand, first of all, see hundreds of images on their page as opposed to a sort of list of 10 at a time, which we know nobody's ever going to go further than the first page. It might help sort of visual exploration become a way just as important as textual search to sort of surface some of the items in our really diverse online collections. And with that, I'll stop.
Thank you so much, Peter. Visually stimulating and impressive as always.
This is the import from IIIF is the Tom Kramer, Josh Hadrow Memorial feature. So.
And I'm sure, speaking for Josh, I think it's probably safe to say we love it. Yeah, Josh already said it. Are there any questions, immediate clarifying questions for Peter before we open it up more broadly? I wonder if each of you could comment on training your own model versus using existing models. Peter, you're maybe this was more about the image segmentation with the Ed Ruscha, but it's how do you approach identifying the features or the objects to work on?
Yeah, you know, I think it's an interesting question. One of the reasons that we have one feature I didn't show today, but is that one of the new features we put into PixPlot is the ability to kind of drag a lasso or a rectangular selection rectangle around images. And one of the reasons we wrote that feature was that we think that it could be really important for people to create their own ground truth, especially folks who aren't as comfortable with a command line. They'll still need a data scientist to help them out to do that kind of work. But in terms of actually putting together the data. But so here's the Smithsonian data set that I shared earlier. And maybe we can jump into a particular area like these jeweled portraits that Kathy curated for us. So in the new version of PixPlot, what you can do is you can basically select some of these, right? You can see that some of my objects on the screen are gaining a kind of yellow or orange boundary, and I can look at the 39 that I've selected, and I can say, well, I don't want that one because it has a different background or something, and then what I can do is I can save as kind of a CSV that will now download into my web browser and contains all of the objects that I had selected. And so what I could do then is something really simple, like copy every file name that I had selected into a new folder called My Training Data for Framed Portraits that are circled or with a black background. Or in a more advanced world, you would have a kind of tensor server on the back end, and you would say, okay, with this JSON array of 39 objects, push those unique IDs back to the server and retrain the last layer of ImageNet or something like that. That would be an exciting additional way to go. I also think, just quickly, that notion of image segmentation is really exciting, and I was really thrilled to see what Smithsonian is doing it in this really kind of specific domain. We lucked out with Ed Ruscha in the sense of, because of self-driving cars, pedestrians and automobiles, there are really good pre-trained models for identifying cars. And so we used actually Matterport's implementation of the mask RCNN visual segmentation stuff, which is based on Microsoft COCO, Common Object and Context. It was really a cheat that we could identify all the cars in 400,000 Ed Ruscha images so efficiently. We were lucky also that the model abstracted back to cars it had never seen. So clearly, I don't think COCO was ever trained on Volkswagen Beetles, but there are a lot of Beetles in 1960s California. And so we got very lucky that it was capable of sort of abstracting back a couple decades in automobile design. We have some folks, including a professor in Germany, who's very interested in retraining a new sort of segmented classifier for certain architectural features in Los Angeles. That's something we're looking forward to trying to help her with. And of course, the Getty Research Institute itself is very interested in those types of custom models. It's sort of it's trite to say, but I think that those scholarly specific or curatorially inflected models are the sort of next frontier in this kind of AI for LAM, because then we break free of the kind of conventional consumerized categories which ship in a lot of the pre-trained models, and we advance kind of the state of art so that it's congruent with the sort of critical direction that archivists and scholars are taking.